What's happening, folks? Geologist Philip Prince got a viewer requested video here. Earthquake in Maine. One occurred this morning, I believe, Monday, January 27th. Why'd this happen? East coast of North America is not supposed to be an earthquake kind of a place, but over the past several years, particularly, there have been a number of notable earthquakes here. The one we're talking about this morning, magnitude four-ish, offshore of Maine, kind of right at the New Hampshire border. I believe, generally speaking, kind of somewhere around where the hand is floating there towards the middle of the screen. Question is, I guess, why are there earthquakes here on the East Coast? I believe Myron Cook just did a video about this as well, so it's something on people's minds. Uh, the answer to that is plate tectonics. Even though the East Coast of North America is quite different from the West Coast, if we zoom out a little bit further here, along the West Coast here, you actually have subduction. It's what we would call an active plate boundary in the sense that one plate, the one under the ocean here, is actually going down under North America, down here along California. You've got that kind of like what we call a strike, slip, or transform type of movement where they're sliding past each other. That's quite different from here on the East Coast. Got all this shallow water, which I'm gonna have a video about coming up fairly soon here. But there is not, a plate going under another one or plates sliding past each other here. We don't really have a plate boundary type of scenario like you see on the West Coast. Now, on the West Coast, that gives you earthquakes and volcanoes. We don't have volcanic activity for sure on the East Coast, but we do have these occasional earthquakes. They're not as big as the ones on the West Coast, which means they don't release as much energy. They tend to be less damaging, although the rocks here on the East Coast are denser, older, colder, and they tend to kind of vibrate better with the energy release of an East Coast earthquake. So you get more bang for the buck in terms of how the shaking is actually felt when it occurs. So the reason we're looking at Google Earth here so zoomed out is that fundamentally to understand why you got earthquakes here on the East Coast, you got to look at plate tectonic layout at the much bigger picture here. And need to start all this off. Mid-Atlantic Ridge, some of it I didn't get up there at the top. You can see all this very beautifully on Google Earth. One of Google Earth's coolest aspects is the fact that you can see the ocean bottom with such great detail. That red area there is a spreading center. That's where the plates are moving apart. Hot molten rock is coming up out of the Earth's mantle, and that's actually producing new ocean bottom and pushing those sides away. And the overall movement here is, you get this kind of bad arrow there. Goodness gracious. Something like that. Okay. And the fact that the Earth's surface is curved kind of complicates things here in terms of representing the directions of the arrows, but you get the basic idea. Spreading ridge of what we call a divergent plate boundary. That kind of outward push there is actually generating what we would call in the geo world compression on the edge of eastern North America. So what that means is the east coast of North America here is sort of feeling pushed in a manner of speaking by the overall stress regime that is generated by the tectonic setup that you're looking at here. So that red line there, the current representation of the mid-ocean ridge, that is sort of the ongoing process that has been happening to open the Atlantic Ocean for about the last 200 million years. Now, what does the future of that look like? Well, eventually, that's going to stop, and this oceanic plate right here is going to start. Clear all the drawings out here. It's going to start sinking down under uh, eastern North America there, and I believe that's what's sort of what Myron's most recent video was about. So that's not happening yet, and that's not going to happen geologically for a while. But the takeaway message is that East Coast of North America feels feels stress kind of like that, right? So it's like it's being squeezed, and the strongest squeezing is generally kind of like parallel to the edge of the continent, right? So that's kind of the framework there. Now, when you have that orientation of stress, that means the rocks down there in the Earth's crust are feeling that stress. The earthquake off the coast of Maine or New Hampshire today was about 13 kilometers deep. It's about 8 miles underneath the Earth's surface. Yeah, that's not terribly deep, but that's getting down into the Earth's crust off the coast like that. The Earth's crust would be, and this is crust, not lithosphere for the sticklers out there. The crust would be, I guess, 25 kilometers thick, like 15 miles thick or something like that. So it would be kind of like maybe halfway down into the Earth's crust or something like that. But despite feeling like solid ground underneath you, and of course, yes, it is solid ground underneath you. The Earth's crust here on the coast of North America, on the East Coast, it is by no means without sort of flaws and weaknesses in it. You can actually see through Pennsylvania here, like kind of these kind of wavy shapes there that are described by the ridges of the valley and ridge. Those are a product of the formation of the Appalachian Mountains. They trend kind of along the margin of the continent here. So you've got all of these weaknesses in there that are a result of I would have to do it like this. I think the continental collision that built the Appalachian Mountains, and then that big mountain range in the middle of the supercontinent Pangea got torn back apart to open up the Atlantic Ocean. That also created a bunch of weaknesses and fractures and whatever else in the Earth's crust. There's a lot of them that oriented kind of like that. So when you think of the East Coast here, just because of all that's happened to it in geologic history, building the Appalachians, tearing that in half to make the Atlantic. Now today, we're we're squeezing all this busted up Earth's crust here, kind of from that direction, right? And when some of those weak spots there that are highlighted in yellow, when those are subjected to this tectonic stress, occasionally they give way and shift and move a little bit, and that's what gives you an earthquake. The earthquakes along the East Coast here, they tend to be, if you were to look at this from the side, they're reverse faults, right? So they're taking that squeezing and turning it into making rock like pop up like that. So it's squeezing, causing a relative like upward movement of rock, if that makes sense. And that's a product again of that stress interacting with all of those broken up rocks there in the Earth's crust. Now, interesting question, like what is underneath the edge of Eastern North America here. A lot of what I do on this channel, of course, is these block diagrams trying to show you what is inside the Earth in a given location. In this particular part of the world, you got all this shallow water here, much deeper water, then you got dry land. Each of those parts corresponds to sort of a different zone in the Earth's crust. And what I just got done talking about here, all these breaks and weaknesses and whatever, those all factor in to sort of defining these different zones. So I'm going to do the paint thing here, draw up a block diagram, sort of what you would see in a cross section, kind of like that, going from like onshore in North America down here to the deep ocean. It's going to show where some of these breaks and weaknesses might be located and give you a sense of what might happen, of course, when you put that stress on the continental margin here that's actually causing these Again, fairly, I mean, frequent might be a wrong word, but we see them with some regularity, but they're fairly small earthquakes, right? So hang on just a minute. Okay, so what is under Eastern North America that gives you that kind of land to shallow water to deep water kind of a setup? Do the typical block diagram thing here. Try to incorporate those characteristics. And hopefully, if I remember to do it, we'll kind of change this thing around a little bit as well to give you a sense of how offshore Maine might compare to other places along the eastern seaboard. Okay. Let's see here. Looks like that's going to work pretty well. Gonna need some kind of a crazy jagged coastline there. And actually going to try to show kind of like water depth here as well. Okay, so let's see if we can fill in some colors here. Earth's mantle, very deep down underneath the Earth's crust. The mantle's green. If you get rock from the mantle and see it at the surface, which rarely happens, tends to be a very pretty color of greens. That's why I do that way. Oceanic crust, that's the black stuff over there. That's going to be some sediment sitting on top of the crust. More on that later. Kind of fill in the water here. Doing pretty well. Make the land surface a slightly different shade of green from the mantle down there. I'll brighten that up a little bit more. Okay, so that worked out pretty well. And kind of the final touches here. I'm going to have some faults here that are breaking up. I don't like that last one, breaking up and thinning that gray rock that is the Earth's crust. The whole idea, the reason there's an Atlantic Ocean is you had a supercontinent, pulled it apart, and that pulling apart took the Earth's crust and stretched it like that. When you stretch rock like that, it doesn't stretch like taffy everywhere. It does down deep, but in the shallower parts of the crust, it breaks apart into little blocks like that, and they sort of slide past each other, and it gives you that kind of thinned out shape. And if you kind of filled this in as a block diagram and see something like something like that right there. So you'd end up with essentially like these tilted blocks, and you can fill those low areas with sediment, and that has happened along much of these coasts. Don't really see that much off the coast of Maine, but most definitely that gray area there is thinned out as you see here, and then down underneath the water, kind of like right as you get to where that black oceanic crust starts up, that's where you get that really rapid deepening, right? So the earthquake off Maine would have happened, I guess, if we drew this in here somewhere, it'd be something like that, as I said earlier, kind of like halfway down in the crust or something like that. I've drawn it there on one of those ancient faults that is a product of the continent splitting apart. Who knows if that's the case, but I've been saying throughout the video, there are so many weaknesses in the rock in Eastern North America just related to its complex history of mountain building and then being pulled apart that there's plenty of options for slippage to occur. All right. Uh, what does this look like in the real world? This picture that I've drawn here. That's basically what you're seeing here as you kind of look along the coastline of Eastern North America, where you've got kind of the full scale crust. The crust has been stretched and thinned here, and then by the time you get out here to the dark blue, that's on top of that black oceanic crust, which is thinner and more dense, and it kind of sags down. That's why the oceans are the oceans, and it stays deep and sag down. You look about 17,000 feet deep where I am right now, all the way out to that mid-ocean ridge that I drew with red, which is only about 9,000 feet deep there. So it's basically a big underwater mountain range right along that ridge. There's kind of fractures coming off of it, what we call transforms, are really, really cool to look at. Again, don't deprive yourself of the opportunity to check these things out with Google Earth. So that's the overall setup, and you can sort of apply this to anything along the East Coast. Now, an interesting kind of addendum here is that in most cases, and apparently the Gulf of Maine is sort of an exception to this. In most cases, you might see this gray crust here kind of sagged down a little bit further. I'm going to see if I can fix this up in an efficient manner here. I don't know. It's going to be tough. So basically, what I'm going to do to it here is turn it into something that is more like what I've got drawn up there in the corner. There's going to be kind of a more exaggerated development of that broken and kind of blocky structure there. And this seems like it's going pretty well. That's going to be filled with all these sediment layers. We'll go ahead and color it in here, and then we'll add some structure to it. Along much of the eastern North American coastline, you have something like this, and within sediments here, you got layers kind of like this that have accumulated, and then all of that is kind of blanketed over top by even younger layers of sediment, right? So you have a structure kind of like that. We'll need to color the rest of that in. And the idea is that in a scenario like this, as more and more of that sediment piles up, because you got rivers kind of flowing off of the continent there, constantly delivering more and more sediment out here to the coastline. Basically, this is a place where you can eventually see the sinking of that oceanic crust starting as a result of the stress direction that I've been talking about, as well as the fact that everything here is just kind of sagging down under the weight of that sediment. Where we are in eastern North America, this sinking process that we've got illustrated here, and that's going to make this really deep ocean trench when it happens. That is kind of on deck geologically, and it's thought that this addition of sediment there can contribute to that process. But ultimately, this oceanic crust just gets old, cold, dense, and starts to sink. So think about it going forward geologically. We might expect to see some kind of like an ocean trench forming there, and when that ultimately happens, you are going to have volcanic development in what is today the East Coast. Again, way down the road. Okay, just sort of thinking about the distant millions of years geologic future there. So clear that out. Go back to paint. So that's the big idea. You're going to see this diagram again here coming down the road, but you have to think about the crust being set up like this. There's all these older structures in it as well from Appalachian development, and they've been broken by these faults. So it's not just uniform rock. When you put that oriented stress on it, I'm talking about, you can get earthquake movement, right? So we'll hop back to Google Earth, keep looking around here. Okay, so that's the big idea there. Interestingly, like I said, off the coast of Maine, where you don't have you don't have those deep Mesozoic basins, you don't see that much online about the structure of that kind of stretched and broken crust there. But if you get down into down here into Jersey, where you had that Tewksbury earthquake last year, which was associated with the Ramapo fault, that's an area that is I mean it's intensively studied because there's such excellent examples of what that stretching and breaking did to the North American crust about again 200 million or so years ago when the Atlantic Ocean was opening. So it's very likely that what you're going to hear is you hear more about this Maine earthquake if anyone puts out more information about it. It may be attached to some kind of an existing geologic structure. I mean, it's basically 100% chance that it is sort of reactivating some kind of a weakness. Exactly what the nature of that weakness is, I admit freely, I do not know. But suffice it to say, this idea of a continent kind of like inheriting almost the effects of past events and those effects controlling how it behaves in the future. That's a really big thing. This sweeping layout that you see in the Appalachians right here. You should probably clear some of that stuff out. So the Appalachians bulge way out there in Tennessee, step back in Virginia, and then they bulge way out there in Pennsylvania again. That's largely a product of what was like what was like the shape or whatever of the margin of the continents that collided to make the Appalachians. So when you actually see the squeezed and folded Appalachian Mountains today, they are showing you their sort of inheritance, if you want to call it that, of a continental setup that's even older. So Earth is always changing, but you can see a lot of geologic history preserved in ways that might not immediately be obvious and from the very big scale, like when you're actually looking down on continents like this. Very interesting idea that deserves mentioning about this. Like what does the future hold? I guess for Eastern North America, Myron did that. He did that very well because it's sort of a different way of thinking about a place like the East Coast. Got that mid-ocean ridge there. Get the red here going again. Mid-ocean ridge there, and you got that kind of pushing away in both directions. Interestingly, kind of off the coast of southwestern Spain and Portugal there, that sinking, what we call subduction, is thought to have already begun. And in 1755, Lisbon, Portugal, was essentially destroyed by an absolutely catastrophic earthquake, had a big tsunami with it. Definitely something in a way, way, way different league from what we see in Eastern North America, but it's in effect the same type of a thing, where the oceanic lithosphere, the oceanic crust there has started to sink, and ultimately that's gonna close the Atlantic back up. So maybe over here we're a little bit behind schedule, but it's reasonable to maybe make a comparison between the two. Don't take out a bunch of new insurance or something like that. That's kind of a way down the road in geologic future kind of thing, right? But good question. I appreciate those questions. I'm gonna try to do a couple more request videos here down the road. Hope you check them out when they come out.